Welcome. This is the Regression Analysis course. My name is Nicoleta Serban. I'm an Associate Professor in the Stewart School of Industrial and System Engineering. The lecture is Model Selection. And in this lesson, I will introduce the general concept of variable selection or model selection along with the objectives, the common objectives in variable selection. In linear regression, the number of predictive variables P, when the number of predictive variables P is large, then we might get better predictions by omitting some of the variables, some of the predicting variables. Models with many predictors have low bias but high variance. Models with few predictors have high bias but low variance. We generally seek to balance a trade-off between bias and variance. Furthermore, when there is multicollinearity among the predicting variables, we can reduce its impact by considering a subset of the predicting variables rather than the full model. This can significantly improve prediction and statistical inference. One also needs to consider the purpose of the analysis. If the purpose is to simply come up with accurate predictions for the response, researchers tend to simply look for variables that are easily obtained that account for a high degree of variation in the response. Most commonly, one would consider a smaller number of predicting variables for prediction versus explanation of the response variable. When the objective is to explain the relationship to the response, one might consider including predicting variables which are correlated, while for prediction this should be avoided. Overall, such objectives are achieved using rigorous variable selection, as we'll learn in this lecture. When selecting variables for a model, one needs also to consider the research hypothesis as well as any potential confounding variables to control for. For example, in most medical studies, age and gender are always included in the model since they're common confounders. Researchers are looking for the effect of other predictors on the response once age and gender have been accounted for. If your research hypothesis specifically addresses the effect of a variable, say expenditure, you need to either include it in your model or show explicitly in your analysis where the variable does not belong. We should always be wary of overinterpretation of the model in a multiple regression setting. Here is why. First, the selected variables are not necessarily special. Variable selection methods are hardly influenced by correlations between variables. Particularly when two predictors are highly correlated, usually one will be omitted despite the fact that the other may be a good predictor on its own. The problem is that since the two variables contain overlapping information, once we include one, the second variable accounts for very little additional variability in the response. Second, if we have a regression coefficient of 0.2 for variable A, for example, the interpretation is as follows. While holding the values of the predicting variables of other predictors constant, a 1 unit increase in the value of A is associated with an increase of 0.2 in the expected value of the response. Lastly, for observational studies, causality is rarely implied. There have been many approaches and advancements toward variable selection. Still, variable selection for a large number of predicting variables is an unsolved problem in statistics. While some of the modern approaches we will learn at the end of this lecture attempt to address this problem, variable selection is an art by itself. In some sense, model selection is data mining. Data miners, machine learners, often work with many predictors. I recommend against blindly and automatically applying variable selection without the learning of the problem at hand, objective of the analysis, variables of interest, underlying hypothesis, among others. All such considerations would lead to a meaningful model and interpretation. Generally, variable selection approaches need to be tailored to the problem at hand. There's no magic bullet. There are no magic procedures to get you the best model. I highlighted this quote in the first lecture of this class, and I come back to this because it's relevant in the context of variable selection. All models are wrong, but some are useful. To begin the introduction of the variable selection methods, I will point out here some notation that will be needed throughout this lecture. Given p predicting variables, we can have 2 to the p combinations of the variables, and thus 2 to the p models to choose from. I denote S a subset of indices in the set 1 to p, with a subset of predictors among the p variables with these corresponding indices. We'll use a notation beta hat S to be the estimated regression coefficients based on the model fitted with the predicting variables with indices in S, or with the XS being the design matrix. Similarly, y hat of S are the fitted values for the same model. I'll refer to this model as well its output as the S submodel. Again, we can have 2 to the p such submodels. In this lesson, I provided the overall framework, the general concept of variable selection. Thank you.